Hello guys, following today's lecture of Stefan Bonte, I would like to continue the discussion of the Higgs boson physics. So the name of the presentation is the Higgs boson physics from the basics to the state of the art. So it's quite a long way to cover, and of course I will cover it only briefly, so that we have 45 minutes and we have to spend only this time. The first question a person encounters when they start learning about the Higgs boson is, why do we need this particle? The answer to this question is the following. In 1964, British physicist Peter Higgs suggested a mechanism according to which elementary particles acquire masses. This theory implies that there is an invisible field. This is called the Higgs field, and this field fills the whole universe, in spite of the fact that we can see it. Some elementary particles catch on this field, and that's why they acquire masses. However, there are some exceptions, because the photon and the gluons don't catch, and that's why they are massless. This is quite a primitive explanation, but I wouldn't like to go into the details like Lagrangians and so on, because it would take too much time. In order to interpret this Higgs mechanism, we can consider the following experiment as it were. We can take a few foam plastic ball sets and put it on the table. Then, if we blow on them like this, they will swiftly fly away because they have very little masses. If the same experiment takes place in water, water will resist the motion of the balls, so that the balls will not move considerably. So water acts as the Higgs field in this case. It gives added masses to the balls, and that's why it prevents them from moving quickly. Also, another important phenomenon occurs when we blow on these balls. There are some little waves, i.e. wavelets, and these little waves correspond to excitations of the Higgs field. And these excitations are called Higgs bosons. So basically, Higgs bosons are like little waves on the surface of water. That's why it's important to have the Higgs boson, because without this particle there is no Higgs mechanism, and we don't know how elementary particles acquire masses. Also, it's interesting to mention that in 1950, two Soviet physicists, Ginzburg and Landau, offered suggested similar ideas in their paper on superconductivity. These ideas looked very close to the basic ideas of the Higgs mechanism, and it shows that if one approach is successful in a certain field of physics, then this approach may be successfully applied in another field. That's why if you know some good approaches, you are free to apply them, and maybe you will get some success. Another point is that the way the Higgs mechanism goes is influenced a lot by the properties of the Higgs boson. That's why it's important to understand these properties in order to better understand the Higgs mechanism. For the clarification of these properties, we may use a lot of models, but the first model to consider is, of course, the standard model, because it's now the main model describing elementary particles and their interactions. And there are very few deviations from this model. It doesn't explain everything, but the things which are explained by this model are usually quite reliable. For the Higgs boson, the standard model predicts that the electric charge is 0, the spin is 0, and the intrinsic and charge parities are 1. We should understand and consider these 4 points separately in order to find what consequences they have. Next. The first property is zero charge. This means that there might be the decay of the Higgs boson to a particle A and its antiparticle A bar. Because in this case, the electric charge will conserve, since the electric charge of the antiparticle is opposite to the electric charge of the particle. So we don't have any violation of the electric charge conservation law. But it's not the only law which governs the decay modes of particles. For example, we don't have transitions like proton to positron or electron to muon and gamma, because the first decay can't take place since the quarks inside proton can't form a positron, and the second decay can't happen because the mass of the electron is much less than the mass of the muon, and that's why the kinematical requirements are not met in this case. So it turns out that in the standard model, Higgs can directly decay to A bar only if A is electron, a quark, the Z or W boson, or the Higgs boson. The latter point is rather interesting because, in principle, Higgs can decay to other Higgs. However, in this case, this Higgs should be off shell, and this reduces the probability of this process a lot. Next. So we can plot the Higgs decay modes. In this picture, we see that it can decay to Z and W bosons, to leptons, to quarks. However, its direct decays to a pair of photons or gluons is impossible in the standard model. These decays can proceed via intermediate W or W bosons or T quarks, because if these particles exchange another particle like this or that, we will have two photons or gluons in the final state. However, the direct decays to photons or gluons are impossible. Next one. Another property of the Higgs boson is zero spin. It means that the Higgs field satisfies the Klein-Gordon equation as any spin zero particle as the wave function of this particle, to be more precise. Here, we should remember that x denotes time and 3 space coordinates, and actually this equation is the basic point of the Higgs mechanism. It is the beginning of this mechanism, so this equation implies that the spin of the standard model Higgs boson is 0. However, this equation affects the Higgs field because it puts certain requirements on this field, and therefore it's a basic origin of the Higgs boson properties. The third property I would like to discuss is the intrinsic parity. Let me remind you what it is. For this reason, we should consider the operator P, such that P acting on a wave function psi returns psi versus Tn minus R. So it runs the radius vector through 180 degrees. If we have an eigenfunction of this operator, and this eigenfunction corresponds to an eigenvalue pi, or sorry, P, then if we apply this operator twice, we will have P squared by psi, according to the first equation. However, on the other hand, the operator P applied twice will run the radius vector through 360 degrees. So the radius vector will not change. And that's why we have that in the end we should obtain the initial function psi. The latter equation gives us the conclusion that P is either 1 or minus 1. Let us recall that the Higgs boson, as any other elementary particle, decays in accordance with the exponential law. So the number of the Higgs boson decreases exponentially with time. In this formula, gamma is called the total width of the Higgs boson, and it can be calculated as the sum over all the final states of the Higgs particle of the partial width of the Higgs boson. It turns out that the fact the intrinsic parity of the Higgs boson is 1 affects the values of the Higgs boson partial width. So this is also rather important for the Higgs pattern. Next one. The last Higgs property is C, which is positive in the standard model. Analogously to the operator E, we define the operator C, which acts on the wave function of a particle A and returns the wave function of the antiparticle A bar. If we consider an eigenvalue of this function, we can apply the operator twice and we will get C squared by CA. On the other hand, we will get CA because this operator, after 2 applications, will return the initial function. Also, we have a conclusion that the value of C can be either 1 or minus 1. Analogously to the P operator, we have the influence of the value of C over the partial width gamma I. Next one, please. That's why the discussion above brings us to the conclusion that to a great extent the electric charge Q determines the Higgs boson decay channels. Of course, this is not the only requirement to know all the decays channel, but in the specific case of the Higgs boson, it goes this way. And the second conclusion is that the properties of spin, parity, and charge parity are responsible for the value of each of the Higgs boson partial widths. That's why if we observe the Higgs boson, we will first prove its existence and neutrality if it decays according to the standard model. And if we measure the Higgs boson partial widths, we will be able to cast some light on the values of the Higgs boson spin, P, and C parities. And after about 50 years after the Higgs suggested his mechanism, in 2012 the Atlas and CMS collaborations working at the Large Hadron Collider observed a neutral boson H, which decayed and according to the predictions of the standard model. This discovery made physicists happy, and Higgs was no exception. Here is he standing in front of a picture of the LHC collider, one of the, LHC detector. However, there are still a lot of things to clarify about the Higgs boson. Later experiments showed that its spin is very likely to be 0 because the probability of this point is about 99%. Next. And the available experimental data are in good agreement with the hypothesis that C and P are positive. However, some other CP scenarios are not yet excluded. And it's quite important to consider the product of the operators C and P. If this product has an eigenvalue alpha, then this number is called the CP parity of the state psi. Analogously to the C and P operator eigenvalues, this eigenvalue can be either 1 or minus 1. If there is no such number, then the CP parity of the state psi is called indefinite. This is terminology which will be then used. And some supersymmetric extensions of the standard model predict that there exist many neutral bosons with indefinite or even negative CP parity. That's why there are some other points of view on the Higgs properties, and it's one of the basic problems now to clarify the CP parity of the Higgs boson. And next, as an example of this study, I'll present you the direction of this work that we are now working on. Next. Since we know that the Higgs boson has zero charge and zero spin, and it's for sure, we will be able to consider a neutral particle X with zero spin, but with arbitrary CP parities, because we would like to clarify the CP properties of the Higgs boson. Then we study the decay of this particle into two Z bosons. Each of these Z bosons is unstable and has to decay into a fermion-antifermion pair. So in the end, we will end up having 4 fermions. These fermions are considered to be non-identical to prevent some calculation problems. Next. The amplitude of the transition X to Z1, Z2 is given by the following formula. The amplitude mostly defines how the decay into two Z bosons takes place. Here we can see 3 terms. P1 and P2 are the momenta of Z1 and Z2, and correspondingly E1 and E2 are their polarization for vectors. So E1 and E2 are well-known functions which can be easily applied for our analysis. What we should have a look at is that each of these 3 terms is proportional to either A, B, or C. And these functions are complex-valued functions of the masses of Z1 and Z2. Since A, B, and C define the scale of the amplitude A, these quantities are often called couplings. So they show how strong is the interaction between the Higgs boson and the 2Z. Also, A, B, and C characterize the CP properties of the boson X. If we don't consider any loops, if we don't consider any loops in our decays, this diagram is called the tree diagram. Next. And for tree diagrams, we have the following correspondence. This is somehow a dictionary between the language of the values of the couplings and the CP properties. So in case when C is equal to 0 and A and B are arbitrary, then we have positive CP parity. In the specific case of the standard model, we have B and C equal to 0 and A equal to 1. Negative CP parity corresponds to the presence of the coupling C and the absence of A and B. Indefinite CP parity means that A and C are not 0 or B and C are not 0. So this is very useful and clear dictionary between the values of A, B, and C and the CP properties. So if we know these couplings A, B, and C, we can tell a lot about the CP parity of the boson X. Then, according to our plan, we have to derive the full distribution of the decay in question. I will later define what the full distribution means. Now you can think about this as the probability of this decay. Experimentalists measure an experimental full distribution. Of course, they consider the case when the particle X is the Higgs boson. The previous slide. There is something hidden here. It means that we have then compare the theoretical and experimental distributions in order to constrain the values of A, B, and C at various masses of Z1 and Z2. So basically our strategy is to obtain the full distribution, compare it with the experiment, and to constrain A, B, and C, therefore getting SCP properties of X. In order to accomplish our plan, we should first consider the momenta of the particle involving in this decay. We all know that the consideration of a decay is usually easier to have a look at when we consider this decay in the rest frame of a decaying particle. Here we can see decaying particles, X, Z1, and Z2. That's why we introduce 3 rest frames. Then we draw the momenta of Z1 and Z2 in the rest frame of X, the momenta of F1 and F1 bar in the rest frame of its parent Z1, and the momenta of F2 and F2 bar in the rest frame of Z2. Having a look at this picture, we can notice that this decay is fully parameterized by only 3 angles. These angles are the following. Theta 1 is the angle between the momenta of Z1 in the rest frame of X and the momenta of F1 in the rest frame of Z1. Analogously, theta 2 is the angle between the momenta of Z2 in the rest frame of X and the momenta of F2 in the rest frame of Z2. The third angle is phi, and it's the azimuthal angle between the planes of the decays Z1 to F1, F1 bar, and Z2 to F2, F2 bar. Basically, this is all we need for angular variables, but there are other useful notations that we can use. We introduce 3 amplitudes, A0, A parallel, and A perpendicular. They are basically proportional to the couplings A, B, and C. Here, A1 and A2 are the invariant masses squared of the Z boson Z1 and Z2. And the function lambda is defined the following way. It's quite well-known kinematical function. Next. Then we can use the formalism of quantum field theory. This theory can give us the function d5 gamma over dA1, dA2, dθ1, dθ2, and d5. This function gives the probability that in our decay, the kinematic parameters A1, A2, θ1, θ2, and phi will have some particular values. So if we want to get the probability of the decay with some certain parameters, we can put their values into the expression for these differential widths, and we will get the probability we are looking for. Using the approximations when we neglect the fermion masses, we have derived the following formula for the fully differential widths. Here we can see functions f1, f2, and so on, f9. There are 9 functions, and they depend on the parameters a1, b2, θ1, θ2, and phi, but they are independent of the Higgs boson couplings A, B, and C. It means that the full dependence on these couplings is concentrated in 9 quadratic combinations. As you can see in this formula, these are these combinations, and they determine the dependence of the fully differential widths on the Higgs boson couplings. It means that if we are able to measure an experimental full distribution, we can compare it with this expression. Then we can constrain these 9 quadratic combinations, and therefore we'll be able to get some constraints on A, B, and C, which is what we want to do. However, now the question arises whether it is possible to obtain a fully differential distribution of this decay. Next. How many decays should be measured for obtaining a precise enough distribution? Well, we can roughly estimate that in order to obtain a distribution of n variables, we need about 10 in the power of n plus 1 decays. It means that for our distribution of 5 variables, about 1 million decays are needed. The next question is how many decays we already have studied. The others and CMS collaborations consider the decay of the Higgs boson to Z1 and Z2 decaying to E minus, E plus, mu minus, and mu plus. And after about 1.5 years of measurements, they have collected data on 26 decays. But we need 1 million decays. It means that we will perhaps have a full experimental distribution, next slide, in 60,000 years. So we will have to hand down from generation to generation the task to measure this distribution if we really want to get it. However, it seems impossible that we will survive 60,000 years, and that's why we have to find some other ways for getting constraints on A, B, and C. We should consider distributions of as little a number of variables as possible. This idea originates from the fact, the previous slide, that the less the number of variables is, the less the number of decays is needed. So if we reduce n, we will have a reduced number of the needed decays. Next. And that's why we consider distributions of a little number of variables. So we first consider the differential widths with respect to A1 and A2. It is obtained by integrating the fully differential decay widths. We can now plot this function if we consider the decay to 4 leptons, for example, which are non-identical in the case when X is a standard model Higgs boson and its mass is equal to the value reported by the particle data group. This distribution means that the probability of the decay to some particular mass, let me tell you this way. So this differential width gives us the probability that the decay will take place with certain values of masses of Z1 and Z2. Here we can see 2 bumps or peaks. The left peak corresponds to the case when the square root of A2 is equal to mz. The right one takes place when the square root of A1 equal to mz. This means that the decays in question happen almost all the time when one of the Z bosons have a mass close to mz. Here mz is called the Z boson mass, but it doesn't necessarily mean that each Z boson has this mass. As we can see from this plot, there are possible cases when the masses of the Z bosons are quite far away from mz. So the decays with one of the Z bosons close to mz are rather probable, but they are not the only thing which can happen. Next. So this basic conclusion that almost every decay in question happens with one of the Z bosons being on shell allows us to obtain other differential widths for our decays. If we obtain them, we can constrain the parameters A, B, and C. Our constraints originate from the data reported by CMS. It tells that the total cross-section of the Higgs production in proton-proton collisions multiplied by the branching ratio of the decay H to ZZ to 4 leptons divided by the same quantity in the standard model is equal to 0.93 plus minus uncertainties. Do you know what is a branching ratio of a decay? So there is no person knowing this fact here. Yeah? Okay, let me explain this way. For example, we have some number of Higgs particles. We will call this number NH, the number of Higgs. There are a lot of them, and some of these particles decay to ZZ and to 4 leptons. The number of these particles will be denoted as NH versus H to ZZ to 4 leptons. If we then divide these two numbers, if we consider the ratio NH to ZZ to 4 leptons divided by NH, this ratio will be called the breaking ratio for this decay by definition. It means that the branching ratio is basically the fraction of particles decaying to a particular decay mode. And of course, these two parameters can be measured in experiments. I use this to be more precise, their ratios can be measured. And after these measurements, CMS gets the following results. We use these results and we constrain the Higgs boson couplings. But before I present our estimates, I should also mention that the Atlas and CMS collaborations have already constrained some of the HCZ couplings. However, the Atlas uses a bit different HCZ couplings: alpha, kappa SM, kappa tilde HGZ, kappa tilde AZZ. These couplings are connected with our couplings A, B, and C via the following linear relations. Since these relations are linear and we have our constraints on A, B, and C, we can easily constrain the Atlas HGZ couplings. Next. The results of our analysis are presented in this table. So the Atlas, CMS, and we consider 3 quantities. These quantities are coupling ratios, and here are some estimates for their 95% confidence level allowed regions. So it means that these quantities lie in the following intervals with a probability of 95%. We can see that all these results are in good agreement, especially it is seen when we compare these two intervals, they almost coincide. However, we also studied a coupling ratio which is not studied by the Atlas and CMS collaborations. Here is our results. So we extended the LHC analysis in this way. In the standard model, each of these quantities is equal to 0, and this supposition is consistent with the results reported by the CMS, Atlas collaborations, and by us. Because these intervals all contain the point 0, which is predicted by the standard model. So as it usually happens, all results are consistent with the standard model, in spite of the fact that there is some considerable improvement in the precision of this result. Also, we should bear in mind that each cell of the previous table is obtained in some particular cases. If we want to perform a more general analysis, we have to apply a different technique. We should recall that the fully differential distribution has 9 quadratic combinations of the amplitudes, and these combinations determine the dependence of the fully differential widths on A, B, and C. We consider the ratios of these 9 combinations to the sum over lambda, the modulus of A lambda squared. And these ratios are called the helicity coefficients. Integrating the fully differential distribution, we can relate all the helicity coefficients to certain observables. For example, if we consider the so-called forward-backward asymmetry of the given decay, we can find that this asymmetry is proportional to the helicity coefficient real part of F parallel star by F perpendicular prime. Here, the amplitudes F are reduced amplitudes, and they are defined in this way to simplify our notations. But basically, they are related to the amplitudes A lambda prime. So we can integrate the fully differential distribution in a similar fashion next. And we will have the following relations between the helicity coefficients and observables. It means that each helicity coefficient is proportional to one or two observables. So if we measure these observables, we will be able to obtain some information on the helicity coefficients. Then we will constrain the amplitudes A lambda, and therefore we will constrain the Higgs couplings A, B, and C, because the amplitudes A are proportional to A, B, and C. That's why the only thing we need to clarify the values of A, B, and C is to measure the suggested observables. These observables are rather interesting, especially some of them next. Here you can see the plots of the most promising observables. They are promising because in the standard model they are all equal to 0. However, in case of some non-standard model CP scenarios, these observables acquire considerable values, as you can see on these plots. So if at least one of these observables is measured to be non-zero, it will mean that the Higgs boson observed in experiments is not the Higgs boson predicted by the standard model. So it will be quite an interesting result. That's why it's of interest to measure these observables at the LHC. Let me remind you the brief content of the CP parity study. In order to clarify the CP properties, we consider a neutral particle with zero spin and arbitrary CP parity. Then we consider the decay of this particle into ZZ decaying to 4 fermions, where fermions are said to be non-identical. Then we constrain the Higgs boson couplings to ZZ. Our constraints are in good agreement with the CMS Atlas collaborations constraint, and also we provide allowed regions for a ratio which is not studied by the LHC collaborations. We also defined observables, measurement of which will allow to get some information on the HCC vertex. An analogous analysis is carried out for the decays into WW, decay into 4 fermions. This analysis allows us to constrain the Higgs boson couplings to WW. The most important conclusion here is the Atlas CMS and our estimates are all consistent with the standard model predictions. And they don't disfavor some CP scenarios. But it is rather fundamental problem because we will always have experimental uncertainties, and we will probably never have only one answer to this problem, that the CP parity is 1 or -1 or something, because there are some uncertainties and we will never be 100% sure about some CP scenario. Next. As a conclusion for the whole presentation, we can say the following. The Higgs mechanism is designed to describe the masses of elementary particles. The properties of the Higgs boson are important to understand exactly how the Higgs mechanism takes place. The Higgs boson has zero charge and zero spin for sure, and it's likely that its C and P parity are 1. However, this is a question for discussion and for next studies, because the CP parity of the Higgs boson is not yet clarified. And this is one of the basic problems to be solved. My final remark is the presented study on the Higgs CP parity is based on the paper which you can see on the screen. Thank you for your attention.